Okay, let's dive right into this explainer. Today, we're tackling one of the biggest needle-in-a-haystack problems in all of analytical chemistry. Now, if you're familiar with chromatography, you already know the whole game is about separating complex mixtures into their individual components. But early on, in ion chromatography specifically, scientists hit a massive roadblock. Getting the ions to separate? That was fine, but actually detecting them afterwards? That was a completely different story. So we're going to look at the brilliant, elegant piece of engineering that actually made modern ion chromatography possible.
Think about trying to hear a whisper at a heavy metal concert. Or, better yet, imagine trying to measure a single specific drop of water right in the middle of a raging thunderstorm. That is exactly the dilemma scientists faced here. The whole method relies on a highly conductive mobile phase, usually a strong acid or a strong base, just to transport the sample through the system. By the time that fluid actually reaches the conductivity detector at the end, the background signal from all those mobile phase ions is literally deafening. You're sitting there trying to detect trace amounts of your target ions, maybe just a few parts per million, inside a solution that is practically screaming with electrical conductivity.
To solve this massive problem, chemists rely on this absolutely ingenious hack called the ion suppressor, and today we're breaking down exactly how it works. First introduced commercially around 1975, this device gets inserted directly between the separation column and the detector. Its entire job, its one and only purpose, is to magically strip away the background noise of the mobile phase while leaving your precious sample perfectly intact and ready to be measured.
Here is our quick roadmap for this explainer. First, finding the signal in the noise. Second, the chemical suppressor solution. Third, the dead volume problem. And fourth, modern membrane suppressors. Okay, section 1, finding signal in noise. Let's see how this noise actually builds up inside the equipment.
Let's use a very specific example from our source material to really ground this. Suppose you are trying to separate a mixture of sodium and potassium cations. To push these through a cation exchange column, you use a mobile phase composed of hydrochloric acid. Makes sense, right? But here's the catch. In this acidic medium, by the time your separated sodium and potassium ions reach the end of the column, they are accompanied by massive amounts of chloride anions and hydrogen ions from that acid. If you were to pass this straight into a conductivity detector, that sheer volume of conductive acid completely drowns out the tiny, faint signal of your sodium and potassium sample. The baseline conductivity is just way too high to see anything useful.
Moving on to section 2, the chemical suppressor solution. The crucial question here is, how do we silence that hydrochloric acid without destroying the sodium and potassium we actually want to measure?
Well, the initial 1975 solution was to add a second column right after the separation column. This was the first chemical suppressor, and it does something so clever. It literally swaps ions to perform an acid-base neutralization. It contains an anionic exchange resin loaded with hydroxide or OH- ions. When that screamingly noisy mobile phase enters, the chloride anions from the acid get trapped or fixed onto the column. In exchange, the column releases those hydroxide ions. Those newly freed hydroxide ions immediately react with the hydrogen ions from the acid. And what do you get when you combine H+ and OH-? You get completely silent, neutral water.
This before and after is just brilliant. Look at the transformation. We go from a deafening background of highly conductive hydrochloric acid straight to silent water. But wait, what happened to our target sample? The sodium and potassium cations just slide right through, but now they pair up with that newly released hydroxide to form sodium hydroxide and potassium hydroxide. And here's the real kicker. These new species actually have a much higher conductivity than their original chloride forms. So we didn't just silence the background noise, we literally amplified the signal of our target species. Talk about a win-win.
You can visualize these exact exchanges happening physically inside the resin. Think of these as microscopic spheres, acting like a chemical sponge. This anionic suppressor column constantly purges the mobile phase of its acidic interference, all while letting those highly conductive target cations slide right on through to the finish line.
Let's hit section 3, the dead volume problem. Because like any first-generation tech, there was a massive catch.
Imagine doing all that precise, incredibly careful work to perfectly separate your sodium and potassium in the first column. You've got them traveling in neat, distinct little bands. But then they enter this bulky suppressor. Because these original suppressors were large secondary columns, they introduced what chemists call dead volume. It's essentially this empty, unoptimized space where fluids can pool and swirl around. So this bulky hardware physically mixed your perfectly separated ions back together right before they hit the detector. It basically undid all the hard work that the first column just accomplished. Super frustrating.
And the dead volume remixing the separated ions wasn't even the only flaw. Think about the chemical exchange we just talked about. Eventually, that resin sponge fills up completely with chloride and totally runs out of hydroxide. So they required constant, periodic regeneration, which completely halted lab work. On top of that, they strictly limited you to isocratic mode. That meant absolutely no gradient dilution. You couldn't change the concentration of your mobile phase on the fly to separate more complex mixtures. So while it was a totally groundbreaking invention, it was highly, highly limited.
Which brings us to Section 4, Modern Membrane Suppressors. How do we keep the brilliant chemistry but ditch the clunky dead volume?
Enter fiber and micromembrane suppressors. Instead of a big, bulky column of beads, the fluid now flows through a microscopic channel bordered by highly selective membranes. And even more mind-blowing, we now have auto-regenerating suppressors. Instead of manually stopping the entire machine to recharge the chemicals, these modern devices literally use the electrolysis of water to regenerate themselves in situ. An electrical current continuously splits water to produce the exact regenerating ions you need, right there on the fly.
The specs on these modern membranes are just incredible. By shrinking that frustrating dead volume down to a microscopic 50 microliters, they completely preserve the perfect separation of the sample. No more swirling and remixing. And because they don't have those large pooling areas, they completely unlocked the ability to do complex gradient elutions. You can dynamically change your mobile phase concentration, and the suppressor just smoothly handles it with negligible baseline drift. It's continuous, it's automated, and it is hyper-efficient.
When you think about trace and ultratrace analysis today, whether that's testing our drinking water for microscopic harmful pollutants or analyzing incredibly complex biological samples in a medical lab, it all relies on this exact technology. It really makes you wonder, doesn't it? As you look at this foundational analytical tech, how much of our modern, safe world depends entirely on this invisible microscopic ability to pull the perfect signal out of overwhelming noise. I hope this explainer helped you visualize exactly what's happening inside the black box of a chromatograph. Keep questioning the invisible processes around you, and I'll catch you in the next explainer.